Alright, welcome everyone to this video. We're going to talk about the fundamental equation and Maxwell's relations. So, what's the fundamental equation? Well, to get what is referred to as the fundamental equation, we first need to start with our first law of thermodynamics, right? Which is du equals dq plus dw, right? And what we'll do is we'll consider reversible change, right, where we've got no extra work, just expansion. Work is happening, and we're going to assume, right, there's no change in number of moles, okay? So, right, if it's a reversible change, that means we're in mechanical equilibrium, so the work done is just minus p dv, okay? If it's a reversible, right, that heat transfer is a reversible heat transfer, so dq reversible is equal to TdS, right? And so that reversible change in internal energy is related with plugging in for what dw and dq reversible are, right? It's just TdS minus pdv. But du is a state function, right? U is a state function, so it can't depend on path. So in general, no matter what the path, du will equal TdS minus pdv, okay? And this is our fundamental equation, okay? Right, and it's considered fundamental equation, right, because it's related with fundamental properties of the temperature, entropy, and pressure, and volume, things like that in the system, related with a change in internal energy, right, not related with this heat and work transfer of energy between systems and surroundings, okay, but more how a change in internal energy is related with a change within your system, okay. So what can we use this fundamental equation for? Okay. Well, if we think, right, we had du in terms of ds and dp, or sorry, ds and dv. So if we think of u as a function of entropy and volume, right, we can write the total differential of u as just du ds plus du dv, right? But again, if we rewrite what that fundamental equation is, we can, it's TdS minus PdV, right? If we compare these two equations, we can see that temperature has got to be the same thing as du ds, and minus P has to be the same thing as du dV at constant entropy, right? Now, U, again, is a state function, okay? And so what that means, right, is U as a state function means we have an exact differential, okay, right, which means that I can take, right, du, d squared u ds dv, and that's the same thing as d squared u dv ds, right? The order of these derivatives doesn't matter, okay? But using the fact that du ds is t and du dv is minus p, we get this relationship that the partial derivative of temperature with respect to volume at constant entropy equals minus the partial derivative of pressure with respect to entropy at constant volume. Okay. These relationships, as well as a few other, are referred to as the Maxwell relations. Okay. We get all of these from looking at internal energy, enthalpy, Helmholtz free energy, Gibbs free energy, things of that nature. Okay. It's where all these end up being derived from, right? Now, these relationships are all true. Every one of these types of changes is always true, no matter what, fundamentally true, okay? But they're not necessarily intuitive. And why is that important? Well, let's say I have some gas, right? And I have some gas, and I'm curious, right? If I do an isothermal process, what is that change in entropy with respect to change in volume, okay? But I can't really measure the entropy very well, okay? Well, I know for that same gas, right, that change in entropy with respect to change in volume at constant temperature is related to its change in pressure with respect to change in temperature under constant volume conditions, okay? And so, right, and so I can understand about how the entropy changes with volume under constant temperature by measuring and observing my gas under constant volume conditions by heating it up and measuring its pressure under those constant volume conditions, right? Right, and essentially that's saying, right, under the constant volume conditions, right, if I take a plot of right, pressure versus temperature, right, and I get some thing, right, the slope, right, at all these different temperatures, right, the slope here is going to be related with this slope of a plot of S versus V, assuming constant temperature, right? So these relationships give us ways of measuring and observing certain things that maybe aren't physically intuitive by looking at more physically intuitive stuff, right? Like, how does volume change with entropy or constant pressure? Well, it's related with the change in temperature or constant pressure with holding entropy constant, okay? Right. So we'll kind of show where the Gibbs Maxwell relations come from, and as well as kind of the like fundamental equation, if you will, for Gibbs free energy, right? So the definition of Gibbs free energy is H minus Ts, and the definition of enthalpy is U plus PV. Okay, so taking the derivative of G here, dG equals dH minus T ds minus S dt. Then plugging in for the fact of what dH is in terms of du plus PV plus VdP, and then using du equals TdS minus PdV, okay, we get dH simplifies down to TdS plus VdP, okay, because plugging this back into here, right, you see that the PdVs cancel with each other, okay, and you're left with just TdS plus VdP. And then we can plug this back in up here, okay? And you'll see that when you do that, right, you'll have a TdS minus TdS, and then you're left with this relationship. That the change in Gibbs free energy, right, is also related with the volume times some change in pressure minus entropy, some change in temperature, okay? And then again, using the fact that, you know, this is our differential for G here, and the fact that G is a state function, okay, we arrive at this relationship between volume and entropy in terms of derivatives of G, and we arrive then at this Maxwell's relation, okay? And so again, these are Maxwell relationships, and how these internal energy and Gibbs free energy and things like that change with pressure and temperature, and say entropy. These relationships will become useful a little bit when we talk about phase changes and phase diagrams and things of that nature, okay? And again, these Maxwell relationships, while we won't really use them much in this class, they are very relevant, you know, in research in terms of being able to relate things that are maybe more difficult to measure and experiments to perform to things that we can easily measure and perform in the lab.